Okay, let's go. Number 1. Match head. Open a kitchen drawer. Somewhere past the takeout menus and the rubber bands and the batteries you're not quite sure are dead, there's probably a box of matches. Pick one up. Look at the tip. That red coating, the part you strike against the side of the box, contains phosphorus. You've done that 100 times without thinking about it, but phosphorus carries one of the stranger unsolved problems in the history of astrophysics. Your body runs on 6 elements: hydrogen, carbon, nitrogen, oxygen, sulfur, and phosphorus. Those are the bioessential elements. Every living thing on Earth requires all 6, no exceptions, from hot spring bacteria to blue whales in the Pacific. Phosphorus locks into the backbone of your DNA. It's the element your cells use to transfer energy. Without it, biology doesn't work. And for most of the history of stellar nucleosynthesis research, 5 of those 6 elements had their origins confirmed through direct astronomical observation. Scientists could point to specific reactions inside specific types of stars and say, that's where your carbon forms, that's where your oxygen comes from. But phosphorus was the holdout. It was the last of the 6 bioessential elements where nobody had directly watched a star produce it. The models said it should form inside core collapse supernovae. The nuclear physics predicted it, but nobody had directly detected it, and for years, nobody did. In 2013, a team led by Ku published a paper in the journal Science, volume 342, that broke the impasse. They pointed instruments at Cassiopeia A, the remnant of a massive star that exploded roughly 350 years ago, about 11,000 light-years from Earth. That expanding shell of debris still glows across multiple wavelengths, and inside it, Ku's team identified phosphorus, not modeled from theoretical calculations, detected in the wreckage. So the case should have closed right there. Supernovae produce phosphorus. The last bioessential element has a confirmed stellar origin. Time to move on. The numbers wouldn't cooperate. What comes next is the part that still doesn't make sense. When astrophysicists tallied up how much phosphorus core collapse supernovae could realistically produce over the full chemical history of the Milky Way, the total fell short. There is more phosphorus in the galaxy than supernovae alone can explain. Some second process, some entirely different type of stellar explosion, had to be contributing through a separate nuclear pathway. And for more than a decade after the Cassiopeia A discovery, nobody could identify what it was. The answer arrived in 2024. A study published on Arxiv identified the missing factory, One Novae. These are thermonuclear detonations on the surfaces of oxygen neon white dwarfs, a specific and relatively uncommon class of dead star. They bear no resemblance to supernovae. They're smaller, faster, far less luminous, but their particular nuclear conditions turn out to be unusually efficient at forging phosphorus. The study showed that One Nova activity peaked roughly 8 billion years ago, precisely the window needed to load the young Milky Way with phosphorus before our solar system formed. And somehow, it gets worse. Even with 2 sources confirmed, phosphorus remains cosmically scarce. To account for the amount that actually exists in our galaxy, you need both of those rare explosive channels operating in parallel across billions of years. Core collapse supernovae and One Novae, running on separate timescales, in completely different types of star systems, producing the same element through independent nuclear reactions. Remove either channel, and the total falls short again. That match in your kitchen drawer holds an element that required 2 distinct types of cosmic explosion and roughly 8 billion years of galactic chemistry to produce. It was the last of the 6 elements your body cannot live without to have its stellar origin directly observed. And until 2013, that observation didn't exist. While scientists were hunting phosphorus in supernovae, a completely different mystery was unfolding in meteorite labs, because the aluminum in your kitchen was leaving behind evidence that shouldn't exist. Number 2. Kitchen foil. Pull a sheet of aluminum foil from the roll, tear it off, hold it up to the light. Every single atom in that sheet is aluminum-27. That's the only stable isotope of aluminum, and it makes up 100% of all natural aluminum on Earth. It formed inside massive stars during carbon burning and neon burning, 2 of the later nuclear fusion stages that run in sequence before a star collapses. But the real story of aluminum in your kitchen is about a different isotope, one that no longer exists anywhere in this solar system. Aluminum-26 was radioactive. Its half-life was approximately 720,000 years. That might sound like a long time, until you consider that the solar system is 4.6 billion years old. After that many half-lives, every atom of aluminum-26 that ever existed here has decayed into something else. It's gone, completely extinct. You cannot find a single atom of it anywhere on Earth, on Mars, on any asteroid, anywhere in this solar system. And yet scientists know, with certainty, that it was here at the very beginning. There's a reason this story is still talked about today. The proof sits inside a meteorite called Allende, which fell in Chihuahua, Mexico, in 1969. Scattered through Allende are tiny mineral structures called calcium-aluminum-rich inclusions, or CAIs. They are the oldest known solid objects in the solar system. When researchers date the formation of anything, the planets, the asteroids, the moons, they measure time from the moment those inclusions solidified. CAIs are time zero. And inside those CAIs, scientists found an excess of magnesium-26. That specific magnesium isotope is the decay product of aluminum-26. The only way to get a surplus of magnesium-26 sealed inside one of the oldest mineral grains in the solar system is if live aluminum-26 was trapped inside when that grain first crystallized. The radioactive aluminum was present at time zero. It got locked into the oldest solids in existence. Then it decayed, atom by atom, into magnesium-26, leaving behind a chemical fingerprint of something that vanished billions of years ago. You'd think someone would have noticed sooner. Nobody did. That magnesium excess sat in meteorite samples for decades before anyone connected it to a long-dead isotope. But here's why the finding matters beyond chemistry. While it was still alive, aluminum-26 was decaying, and radioactive decay releases heat. In the first few million years of the solar system, when the planets hadn't formed yet and everything was loose rubble, aluminum-26 was the dominant heat source, melting and differentiating the young planetesimals. It's the reason those early rocky bodies developed iron cores surrounded by silicate mantles instead of remaining undifferentiated lumps of mixed rock and metal. The layered interior of the planet you're standing on right now traces back to the thermal energy released by an isotope that went extinct billions of years before anything alive existed here. In 2023, a study published in Nature Communications examined a meteorite called Erg-Chech 002 and added a complication. Aluminum-26 was not evenly spread across the early solar system. Its distribution was heterogeneous. Some regions received more, some received less. The implications are still being sorted out, but the finding suggests the heating wasn't uniform. Different zones of the early solar system were processed by different amounts of decay, heat, which may help explain why the rocky inner planets turned out so different from one another, despite forming from the same disk of material. That sheet of foil in your hand is aluminum-27, stable and unremarkable, the version that survived, while the isotope that vanished is the one that shaped everything. Its decay heated the first rocks, melted the first planetesimals, and gave Earth the layered interior that makes plate tectonics and magnetic fields possible. The evidence is a faint surplus of magnesium-26, locked inside grains older than any planet. The decay heat separated the first rocks into layers. Iron sank to the center, but where did the iron come from? The answer involves a pan on your stove. Number 3. Iron skillet. Pick it up, go into the kitchen, grab the cast iron skillet off the stove or out of the cabinet, and hold it in one hand for a second. Feel how heavy it is. That weight, that specific density you notice every time you lift it, traces back to how iron atoms are packed together at the nuclear level. And the story of how they got packed that way is one of the most violent things that has ever happened anywhere. Iron-56, that's the isotope in your pan. 56 nucleons, 26 protons, and 30 neutrons, held together with a binding energy of 8.79 million electron volts per nucleon. That number matters because it's the highest of any element on the periodic table. Iron-56 is the most tightly bound, most stable atomic nucleus in the universe. Nothing holds together better. And that stability is the entire reason it ended up in your kitchen. Because Iron-56 is the last thing a massive star can build before everything falls apart. Stars spend most of their lives fusing hydrogen into helium. If you're the sun, that's all you'll ever do. Burn hydrogen for 10 billion years and then slowly fade out. But if you're a star 8 or 10 times more massive, the story is very different. Once your hydrogen runs low, you contract, heat up, and start fusing helium into carbon, then carbon into neon. neon into oxygen, oxygen into silicon. Each stage burns hotter and faster than the one before. The hydrogen phase lasts millions of years. The helium phase lasts hundreds of thousands. By the time you reach silicon burning, the final stage, you've got about a day left. And then the star made the one decision that changed everything. It fused silicon into iron. And that was the end of the line. Because iron sits at the absolute peak of the binding energy curve. You can't get energy out of fusing iron into anything heavier. You can't get energy out of splitting it into anything lighter. Iron is the ash. The dead end. When the core fills with inert iron and nickel, fusion stops cold. And without the outward pressure of fusion to push back against gravity, there is nothing holding the star up anymore. The core holds together for a few moments, maybe milliseconds, and then it crosses a threshold called the Chandrasekhar mass limit, roughly 1.44 times the mass of our Sun, all compressed into a volume about the size of Earth. Once it passes that limit, electron pressure can no longer support it. The core collapses. In under 1 second, the inner core goes from roughly the size of Earth to about 10 miles across. The outer layers of the star, still falling inward at a significant fraction of the speed of light, slam into this suddenly rigid core and rebound outward. That rebound is the supernova. And no, I'm not making that up. Under 1 second. A stellar core with more mass than our Sun compresses to the size of a small city in less time than it takes you to snap your fingers. If you want to keep finding out what's hiding inside the ordinary things in your house, subscribe. The energy released is staggering. Just the photodisintegration process, where the explosion tears apart the very iron nuclei the star just spent its life building, costs roughly 1.7 times 10 to the 51st erg for every tenth of a solar mass of iron in the core. But here's the part that connects back to your kitchen. The iron in your pan wasn't actually forged as iron, not directly. In the extreme conditions of the supernova blast, what gets produced in enormous quantities is nickel-56, radioactive, unstable. It decays first to cobalt-56 with a half-life of 6.1 days. Then the cobalt decays to iron-56 with a half-life of 77.1 days. So the iron atoms in your skillet started as nickel billions of years ago, inside the expanding debris cloud of a star that had just torn itself apart. They became iron over the course of a few months of radioactive decay, drifting through space in the wreckage of a dead sun. You can season that pan however you like. Rub it down with oil, bake it at 450. But the atoms you're seasoning were assembled at temperatures that would make your oven look like the inside of a freezer, inside a star that no longer exists anywhere in the sky. Iron was the end of the line for the star. But the shock wave that scattered it forged something else entirely. Something that ended up in every wall around you. Number 4. Plaster wall. Knock on the wall nearest you. That hollow thud is drywall. Sheets of compressed gypsum, sandwiched between paper, nailed to a wooden frame. Run your hand across it. Smooth, slightly chalky, about half an inch thick. It's been the standard wall material in American homes since the mid-20th century, because it's cheap, it's fire-resistant, and a crew can hang an entire room of it in an afternoon. But strip away the paper, and what you've got is gypsum. Calcium sulfate dihydrate, CaSO4, 2H2O. The calcium in that formula is what matters here. 96.9% of all natural calcium on Earth is a single isotope, calcium-40. And calcium-40 was forged in the final seconds of a star's collapse. In the last section, we talked about a star building up layers of elements through nuclear fusion, one shell at a time. That's the steady process. A star converting lighter elements into heavier ones over thousands of years, layering them in concentric shells around its core like an onion made of nuclear fire. Carbon on the outside, oxygen beneath it. Neon, then silicon, then iron at the center. Patient, methodical. Almost elegant, if you can call thermonuclear fusion elegant. Calcium-40 formed differently in the shock wave itself. When a massive star, something more than 8 times the mass of our Sun, finally runs out of fuel, the iron core it spent millions of years constructing collapses inward. The collapse takes milliseconds, and the rebound sends a shockwave tearing back outward through every one of those carefully layered shells. That shockwave doesn't just scatter the material, it compresses it, superheats it, and when it rips through the oxygen-rich layer, it triggers a completely new phase of nuclear fusion. Explosive oxygen burning. This is not the patient process that built the shells over millennia. This is shock-driven. It begins and ends in seconds. The temperature spike in those few seconds exceeds anything the star achieved during millions of years of steady fusion. The difference matters. Hydrostatic burning works like a furnace, slow and steady. Explosive oxygen burning hits fast, like a detonation, and it's dramatically more productive. Stellar nucleosynthesis models show that elements in the oxygen to calcium mass range are overproduced by a factor of 2 to 3 during this shock-driven phase, compared to what hydrostatic burning alone would yield. In a handful of seconds, the shockwave manufactures more calcium than the star's steady fusion produced across its entire lifetime in that layer. So you've got calcium-40 atoms, freshly forged in a supernova shockwave, blasted into interstellar space at thousands of miles per second. Here's what happens next. They slow down. They cool. Over tens of millions of years, they mix with hydrogen gas and dust from other dead stars drifting through the interstellar medium. Gravity pulls that material together into a dense molecular cloud. The cloud contracts. A new star ignites at its center. The leftover debris flattens into a spinning disk, clumps into rocky worlds, and one of those worlds becomes Earth. The calcium settled into the planet's crust and dissolved into its oceans. Ancient seas, shallow and warm, evaporated under a younger sun, and the dissolved calcium bonded with sulfate ions and water molecules to crystallize into gypsum. Layer after layer, buried under sediment and compressed for hundreds of millions of years into thick evaporite deposits underground. Today we mine those deposits. We heat the raw gypsum to drive off some of its water, grind it into powder, mix it with water, press it flat between sheets of paper, and let it harden. That's a sheet of drywall. Every wall in a modern American home is covered in it. Bathrooms, bedrooms, hallways, ceilings. Supernova ejecta to interstellar dust cloud to early Earth, to ancient seabed to gypsum mine to your wall. Your walls are made of supernova shrapnel, and you've been putting shelves on them. The calcium needed one shockwave. The 2 atoms in your table salt needed 2 completely different nuclear furnaces inside the same dying star. Number 5. Grain of salt. Reach for the salt shaker on your table. Pick it up. Shake it once over your palm. Those tiny white crystals are sodium chloride. NaCl. 2 elements. 1 atom of sodium, 1 atom of chlorine, bonded together and repeated billions of times in a crystal lattice small enough to sit on your fingertip. Those 2 elements were made inside the same dying star, but not in the same place. The salt in your shaker was mined from halite deposits. Halite is rock salt, left behind when ancient bodies of water evaporated and their dissolved minerals crystallized into massive beds of white stone. Some of these deposits formed during the Permian period, hundreds of millions of years ago, before dinosaurs walked the earth. Others are older still. They sit hundreds or thousands of feet underground, and we extract them with heavy machinery or dissolve them with injected water and pump the brine to the surface. The atoms in those crystals are far older than any rock on this planet. Start with the sodium. Every sodium atom on Earth is sodium-23. It is the only stable isotope of sodium that exists anywhere in the universe. And it formed during carbon burning, a nuclear fusion process that occurs deep inside a massive star when core temperatures reach roughly 800 million Kelvin. At those temperatures, carbon-12 nuclei slam into each other with enough energy to fuse. When 2 carbon-12 nuclei merge, several outcomes are possible. One of them ejects a proton and produces sodium-23. Physicists write it 12C, 12C, P, 23 Na. That's 1/2 of your salt molecule, the sodium half, forged in the carbon-burning shell, which sits in the outer regions of the star's layered interior. But the star wasn't done yet, not even close. The chlorine half came from deeper inside, from a hotter layer, from a fundamentally different set of nuclear reactions. Chlorine has 2 stable isotopes, chlorine-35 and chlorine-37. They formed through 2 distinct pathways, both occurring during oxygen burning, a process running in a shell closer to the star's core than the carbon-burning shell where the sodium was made. Hotter, denser. A different world entirely, separated from the sodium's birthplace by what might have been a few thousand miles of stellar interior, but might as well have been a different universe in terms of conditions. Chlorine-35 formed when protons were captured by sulfur-34 nuclei under those extreme conditions. Chlorine-37 took a more roundabout path. Neutron capture on argon-36 produced argon-37, which is unstable. Argon-37 decayed into chlorine-37. 2 isotopes, two nuclear pathways, both happening in the oxygen-burning shell at temperatures that dwarf the 800 million Kelvin needed for carbon burning. That's the kind of number that makes chemists lose sleep. Two atoms sitting right next to each other in every grain of salt you've ever tasted, and they were forged in two completely different nuclear furnaces inside the same star. The sodium came from carbon burning in an outer shell. The chlorine came from oxygen burning in a deeper, hotter shell. Different fuels at different temperatures, running completely different reaction chains to produce completely different products. Same star, one molecule, two atoms, two burning shells. Then the star died. It exploded, and both elements launched into interstellar space, along with everything else the star had manufactured across its lifetime. They drifted for millions of years. They mixed into the molecular cloud that eventually collapsed under its own gravity and formed our solar system. Both elements accreted into the young Earth. Both dissolved into the planet's early oceans. And when sections of those ancient oceans, shallow basins cut off from the larger body of water, evaporated under the heat of a younger sun, the sodium and the chlorine found each other. They bonded into crystals of sodium chloride. They settled into layers of halite. Those layers were buried under sediment, compressed over hundreds of millions of years into the deposits we mine today. You pick up the shaker without a second thought. You shake it over your dinner. One of those atoms came from the carbon-burning shell, the other from the oxygen-burning shell, reunited in a white crystal billions of years after the star that made them both tore itself apart. Your salt dissolved in ancient oceans. But the water in those oceans had an origin story of its own, and it didn't start on this planet. Number 6. Faucet water. You turned on a faucet this morning. Maybe you filled a coffee pot. Maybe you just let the water run over your hands while you were still half asleep, waiting for it to get cold. You didn't think about where it came from. Nobody thinks about tap water. But some of what flowed out of that faucet didn't come from a reservoir. It didn't fall as rain. It arrived on asteroids, billions of years ago. That sounds like something you'd hear from a guy at a party who's on his third drink. But there's real chemistry behind it. Measurable, repeatable chemistry. And it begins with a single ratio. Every water molecule has hydrogen in it. That's the H in H2O. But not all hydrogen atoms are identical. Some carry an extra neutron, which makes them roughly twice as heavy. That heavier version is called deuterium. And the proportion of deuterium to ordinary hydrogen in any sample of water is called the DH ratio. Think of it as a fingerprint. It's unique to where and how that water formed. Comets carry one DH signature. Asteroids carry a different one. Earth's oceans carry their own. For decades, scientists assumed comets delivered the water. The logic seemed airtight. Comets are essentially giant dirty snowballs, loaded with ice, swinging through the inner solar system on long elliptical orbits. If you needed something to deliver water to a young planet, comets looked like the obvious candidate. But when researchers finally measured the DH ratio in cometary water, it came back wrong. Too much deuterium. The fingerprint didn't match. Comets were out. So where did Earth's water actually come from? In December 2020, a Japanese spacecraft called Hayabusa 2 returned to Earth, carrying about 5.4 grams of surface material from a near-Earth asteroid named Ryugu. That's less than a quarter of an ounce. You could lose it between your couch cushions, but it was enough to run isotope analysis on. Then in September 2023, NASA's OSIRIS-REx mission touched down in the Utah desert with its own sample, collected from a second asteroid called Bennu. 2 spacecraft, 2 different asteroids. 2 independent sample sets returned to Earth 3 years apart. Both told the same story. In December 2022, a team led by Richard Greenwood published their findings in Nature Astronomy. They had analyzed the oxygen isotope ratios in the Ryugu samples and found they were a near-perfect match to a group of meteorites called Ci carbonaceous chondrites. These are among the most chemically primitive materials ever studied, and critically, the water locked inside them carries a DH ratio that aligns with Earth's oceans almost exactly. That was only round 1. The DH result confirmed the hydrogen fingerprint, but the oxygen isotope data from Greenwood's team provided a completely independent second line of evidence. 2 different elements, 2 different isotope systems, both pointing to the same conclusion. C-type asteroids delivered Earth's water, and that ruled comets out for good. I mean, think about that for a second. The water in your glass right now carries the same isotopic signature as material scraped off the surface of a rock drifting through space. And it didn't arrive in one delivery. It accumulated over billions of years of bombardment, impact after impact. Carbonaceous asteroids slamming through the atmosphere of a planet that was still molten, still forming its crust, each one carrying traces of water trapped inside its mineral structure. The early Earth was far too hot to hold on to anything as light as water vapor. Surface temperatures during the first few 100 million years would have driven off any water the planet started with, boiled into space and gone. So the water that's here now, filling every ocean on the planet, feeding every river, sitting in every aquifer, running through every pipe in your house, nearly all of it was delivered afterward, added from outside, carried in by C-type asteroid bombardment over a timespan so vast it almost refuses to fit into a sentence. And yet here you are, standing at the kitchen sink at 6 in the morning, filling a glass with it, running it through a filter, complaining that it tastes like chlorine. The water in your glass is asteroid water, cycling through the planet's rock and atmosphere for roughly 4 billion years. It just happens to come out of copper pipes now. The asteroids brought the water. But locked inside meteorites from the same bombardment, scientists found grains of something older than the sun itself. Number 7. Silicon chip. The chip running your phone right now is made of silicon, specifically silicon-28, 28 nucleons in each atom. And every single one of those atoms was forged inside a dying star, in a shell burning at roughly 2 billion degrees Kelvin. That temperature matters. At 2 billion Kelvin, oxygen nuclei have enough kinetic energy to overcome their mutual electrostatic repulsion and slam into each other. When two oxygen-16 nuclei fuse, one of the products is silicon-28. This reaction, oxygen burning, happens in a thin shell wrapped around the core of a massive star in its final stages. Not at the center. The center is already filling with iron by that point. Silicon forms one layer out, in a region so hot and compressed, it's difficult to compare it to anything you've ever experienced. And the clock on it is brutal. The oxygen-burning shell, the forge that produced the silicon in your phone, lasts roughly a year before the star dies. 1 year. 1 year of fusion at temperatures beyond comprehension, and then the core collapses and the entire structure blows apart. The silicon gets launched into interstellar space along with everything else the star ever made. Now, you might reasonably ask how we actually know this. It's one thing to describe what should happen in a theoretical model of a stellar interior, but is there physical proof? Something you can hold in your hand? There is, and it fell out of the sky in 1969. On September 28, 1969, a fireball streaked across the morning sky near the town of Murchison in Victoria, Australia. The meteorite that struck the ground turned out to be one of the most scientifically important rocks ever recovered. Inside it, researchers found something they weren't expecting. Tiny grains of silicon carbide, some of them smaller than a single human cell. These weren't ordinary mineral crystals that formed in our solar system. They were pre-solar grains. Material that existed before our sun was born. The real question is what happened inside that shell? What trace did it leave behind? And in 1987, 2 teams found the answer. Ernst Zinner and his group at Washington University, along with Ed Anders and his team at the University of Chicago, published findings that changed how we understand the origin of solid matter. They had analyzed the SiC grains from the Murchison meteorite and found that the isotope ratios were wrong. Not wrong as in contaminated or poorly measured, wrong as in foreign. The ratios of silicon isotopes, carbon isotopes, and nitrogen isotopes locked inside these grains didn't match anything else in our solar system. They matched the predicted output of specific layers inside a supernova. If you want to keep finding out what's hiding inside the ordinary things you use every day, subscribe. Later researchers went further using an instrument called the nanosims, a specialized ion microprobe capable of measuring isotope ratios in objects smaller than a grain of sand. When they turned it on the Murchison SiC grains, the results were definitive. The anomalous isotope signatures could be traced not just to supernovae in general, but to specific shell layers within them. The same oxygen-burning shells where silicon-28 is theoretically produced. Theory and physical evidence, lining up. And then there's the age. These grains are between 5 and 7 billion years old. Our sun is about 4.6 billion. That's not a typo, by the way. 5 to 7 billion years. The silicon carbide grains sitting inside the Murchison meteorite are older than the Sunday. They survived the formation of our entire solar system. They got swept into an asteroid, drifted through space for billions of years, and eventually landed in a sheep paddock in rural Australia. And locked inside them is the same element that's running the processor in your pocket right now. You're swiping through a phone built from dead stars. The silicon was forged at 2 billion degrees in a shell that lasted about a year. It was blasted into space by a supernova. It drifted. It got incorporated into the cloud of gas and dust that eventually became our solar system. And roughly 5 billion years later, someone in a clean room etched circuits into a wafer of it so you could check your email on the train. Up to this point, every item on this list was forged inside a dying star. The next one required 2 dead stars to collide. Number 8. Gold contact pins. Pick up your phone. Look at the charging port. Those tiny contact pins inside it are plated in gold. So are the connectors inside your laptop, your TV, your router, the pins on every memory module in your desktop computer. Everywhere an electrical signal passes through a junction that has to work reliably for years, manufacturers plate the contact in gold. It doesn't corrode. It doesn't oxidize. It maintains conductivity decade after decade. That's why every circuit board in your house depends on it. That gold exists because 2 dead stars spiraled into each other and collided. Everything we've covered so far came from stars that died alone. A single massive star that burned through its fuel, built up concentric shells of increasingly heavy elements, and scattered them when it exploded. A supernova can forge phosphorus, calcium, silicon, iron, and dozens of elements in between, but gold is beyond it. The problem is neutrons. Gold sits at atomic number 79 on the periodic table, near the upper end of the naturally occurring elements. To build a nucleus that heavy, you need to bombard a lighter nucleus with neutrons faster than that nucleus can decay. You need to bury it in neutrons so rapidly that it has no time to shed particles and settle back into something lighter. This process is called the R process, rapid neutron capture. And the neutron flux it demands is so extreme, so far beyond what a supernova produces, that for decades astrophysicists were stuck. They knew the R process had to be happening somewhere. The math required it. The gold in Earth's crust required it. But no one had ever directly observed it taking place. The theoretical models pointed to one candidate: neutron star mergers, 2 stellar corpses, each one the collapsed core left behind after a supernova, spiraling together under their own gravity and colliding. The conditions inside that collision, the unimaginable density of neutron-degenerate matter tearing apart at close to the speed of light, could theoretically generate the neutron flux the R process demands. But theory and observation are 2 different things. And that wasn't even the part that got people excited. August 17th, 2017. The LIGO detectors in Washington State and Louisiana, along with the Virgo detector in Italy, picked up gravitational waves. Not from merging black holes, which is what they'd been built to find. This signal was different, longer, lower frequency. It matched the signature of 2 neutron stars, each roughly the mass of our Sun, spiraling toward each other in a distant galaxy. The event was designated GW 170817. Almost simultaneously, NASA's Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of sky. GRB 170817A. Within hours, observatories on every continent and in orbit swung their instruments to the same coordinates and found a new point of light that hadn't been there the day before. A kilonova, designated SSS-17A. The visible light afterglow of 2 neutron stars ripping each other apart. This was the first time in the history of astronomy that a single event had been confirmed through 3 completely independent channels at once. Gravitational waves rippling through space-time, gamma rays crossing the electromagnetic spectrum, and visible light from a ball of newly forged radioactive matter that hadn't existed 24 hours earlier. Multi-messenger astronomy went from theoretical concept to proven reality in a single night. And the kilonova's light told the real story. Its spectral signatures matched the fingerprints of freshly synthesized heavy elements. R process elements. Gold, platinum, uranium. The estimates published by Kaslawal and colleagues in Science that same year put the yield at 0.03 to 0.06 solar masses of R process material. To make that number concrete, That single collision produced somewhere between 10,000 and 20,000 Earth masses of heavy elements. Edo Berger, an astronomer at Harvard, put it simply. The ejected material, he said, will eventually combine with other material to form stars, planets, life, and jewelry. 2 collapsed stars, each the mass of the Sunday compressed into spheres the size of a city, spiraling into each other at a third the speed of light. And the debris from a collision just like that one, billions of years before anyone was around to point a detector at the sky, drifted into the cloud of gas that became our solar system, accreted into Earth's crust, got mined, refined, and deposited in a layer a few atoms thick onto the contact pins of your phone charger. You plug it in every night without thinking about it. The gold came from a collision in deep space. The next piece of evidence came from a collision with Earth. Number 9. Window glass. Sunlight is coming through your window right now. Or if it's nighttime, it came through this morning. Either way, you look through glass today. And glass, at its simplest, is silicon dioxide, the same compound that makes up quartz and sand. You already know from earlier on this list where silicon comes from. But there's one piece of glass on Earth with a story the others can't match. Scattered across thousands of square miles of the Western Sahara, in the sand seas along the Libyan-Egyptian border, you can find pale yellow chunks of nearly pure silica glass. They're called Libyan desert glass, and they formed approximately 29 million years ago. That date alone raises a question. So does the temperature. To produce glass this pure, you need sustained heat above 2,900 degrees Fahrenheit. For reference, the hottest igneous rocks on Earth, fresh Hawaiian basalt pouring out of an active volcano, top out around 2,200 degrees Fahrenheit. Nothing in Earth's interior gets hot enough. And there's no volcanic activity in that part of the Sahara. There wasn't 29 million years ago either. So something else produced the heat. For decades, scientists debated what. Lightning was the first candidate. It does produce glass. When a bolt hits sand, it fuses the grains into a jagged, hollow tube called a fulgurite. But fulgurites are tiny, irregular, nothing like the broad sheets of Libyan desert glass blanketing the desert. Lightning couldn't account for the scale or the purity. An asteroid or comet impact was the obvious alternative, but there was a problem there too: no crater. The Sahara has been searched repeatedly, and no confirmed impact structure in the right location, at the right age, has ever been found. Without a crater, the impact hypothesis stayed in the category of educated guess. Then, in 2019, Cavosi and Koberl published a study in the journal Geology, Volume 47, Number 7. They examined the glass at the microscopic level and found rhyodite. Rhyodite is a high-pressure polymorph of zircon. That means it's a form of zircon that only exists when zircon has been subjected to extreme shock pressures. And rhyodite has one known formation mechanism: hypervelocity impact. Nothing else on Earth produces it. Not volcanism, not lightning, not tectonic pressure. The presence of rhyodite in Libyan desert glass confirmed that the glass was created by something hitting the desert at cosmic speed 29 million years ago. The crater may have eroded or been buried under sand, but the mineral evidence doesn't need a crater. Rhyodite proved it happened. And the timing of what happened next? Almost too perfect. In 1997, a mineralogist named Vincenzo de Michele was examining artifacts at the Egyptian Museum in Cairo. He stopped at the pectoral of Tutankhamun, the ornate chest piece buried with the boy king over 3,300 years ago. At the center of the pectoral sits a carved scarab beetle. It had been catalogued for decades as chalcedony, a common form of quartz. De Michel looked closer. It wasn't chalcedony. It was Libyan desert glass. Someone, likely a craftsman working in the workshops of the 18th dynasty, had taken a piece of pale yellow glass from the deep desert, carved it into a sacred beetle, set it in gold, and placed it on the chest of a pharaoh. It remains the only confirmed use of Libyan desert glass in any ancient Egyptian artifact. 29 million years in the desert, then a teenager wore it on his chest. Follow the chain backward. A hypervelocity impact strikes the Sahara 29 million years ago and turns the sand to glass. The glass sits in the open desert for 29 million years, weathered but intact. An artisan finds a piece, carves it, and sets it in gold. The gold goes into a tomb in the Valley of the Kings. The tomb stays sealed for 33 centuries. And the glass that started with something from space ends up behind museum glass of a different kind. Scientists said for decades that you couldn't find space material in a city. One man proved them wrong. Number 10. Shelf dust. Run your finger along the top of a bookshelf. Look at what collects on your fingertip. Gray, fine, unremarkable. You'd wipe it on your pants and move on. But some of what you just touched is not from Earth. Every year, approximately 5,200 tons of extraterrestrial dust reaches the surface of this planet. That number comes from a 2021 study by Rojas, Duprat, and colleagues based on a collection program that ran for roughly 20 years at Concordia Station, a research base at Dome C in Antarctica. They chose Antarctica because the ice is clean. There's no soil, no industrial contamination, no leaf litter. Anything that lands on the surface and isn't snow came from somewhere else. And what they found, grain by grain, was space. The particles are small, mostly microscopic, and they fall everywhere, not just Antarctica. Everywhere. Your roof, your yard, your bookshelf. That's about 14 tons a day reaching the surface of the Earth. Every day, including today. For a long time, the scientific consensus was that you could only collect this material in pristine environments. Antarctica, the deep ocean floor, places with no human contamination. The idea that you could find micrometeorites in a city was considered by the relevant experts to be impossible. The background noise of urban pollution, industrial particulates, brake dust, construction debris would drown out anything extraterrestrial. A Norwegian jazz guitarist named John Larsson disagreed. Starting around 2010, Larsson began a project he called Project Stardust. He collected sediment from rooftop gutters, not in Antarctica, in Oslo, in Paris, in Berlin, gutters on ordinary buildings in the middle of major European cities. He filtered the material, sorted it under magnification, and started finding spherical, partially melted particles with iron-nickel compositions and silicate inclusions. They looked exactly like what the Antarctic researchers were finding. And they shouldn't have been there. Larsson partnered with Dr. Matthew Genge at Imperial College London. Together, they confirmed what Larsson had been finding. The results were published in the journal Geology. Over 1,000 confirmed urban micrometeorites, collected from city rooftops, verified through the same analytical methods used on Antarctic samples. And this is the part where it stops being abstract. Some of those micrometeorites contain presolar grains. These are tiny mineral inclusions that formed before the solar system existed. They condensed in the outflows of older stars, survived the collapse of the gas cloud that became our sun, survived 4.6 billion years of solar system history, entered Earth's atmosphere, and landed on a rooftop in Oslo. They are older than the sun, older than every planet, and they are sitting in the gutter dust of apartment buildings. You dusted your shelf last week. Some of what you wiped away was older than the solar system. Every other item on this list arrived in the past, but the dust is different. It's still arriving, 14 tons of it today alone, while you're watching this. Your home is a museum of the universe's most violent history, and you just didn't know you were living in it. Subscribe if you want to keep finding out what's hiding in plain sight. Leave a comment telling me which one surprised you most and where you're watching from.